Now, we will gather some tools from multivariable calculus to deal with the next problem. So, first recall that the total differential of phi, right, it is this one, dou by phi over dou by x times dx. I mean, this happens like this. The rate of change with respect to x of phi is this one, once the other variables are fixed. Now, if you change, now this is the rate of change. If you change x by a infinitesimal amount, this is a total change due to x. Similarly, this is the rate of change of function phi once the other variables are fixed. Now, with that setup, if you change y a little bit, this is a total change due to y, because this is the rate of change, this is a change of y. So, this is a total change. Similarly, if you fix the other two variables, namely x and y, the rate of change is this. Now, this is the infinitesimal change of z. Therefore, the change due to that infinitesimal change of z is the product of these two. So, the total change is this once x, y and z are changed by small amounts. So, this is a total this is a total differential. Also note that if you have a product like this, the derivative can be obtained in two ways, like x times the derivative of y, so x times dy, plus y times the derivative of x, or you can use this one. Look, if this is phi, the partial derivative of this with respect to x is y. So, you have y times dx here. Similarly, partial derivative of this expression with respect to y. Now, see, there x is treated as a constant, therefore, x times dy. Likewise, I mean here straight away you can do this, x squared times derivative of y dy, y times the derivative of this, y times the derivative of x squared is 2x, therefore, 2x dx, y times 2x dx. Here you have again a product, you have x cubed times y squared, therefore, you can do it like this, x cubed times the derivative of y squared, that is 2y dy, then y squared times the derivative of this, y squared times 3x squared dx. So, if you can simplify this into this one, or you can do it in this way as well. The partial derivative of this with respect to x should be 3x squared y squared, because there y is treated as a constant. So, 3x squared y squared. Likewise, you can get this term by differentiating this with by partially differentiating this with respect to y. So, you have 2y x squared, look 2y x squared, x cube, 2y x cube here. Now, if you have all three variables, you can do it like this. For example, partial derivative of this one with respect to x, this one. So, these two are treated as constants. So, you get y z, because y z is a constant, times x, it is like 4x, the derivative is 4. Likewise, here it is y z. Similarly, if you partially differentiate with respect to y, x and z are constants, therefore, it is like a constant times y. So, the derivative is the constant. So, x z times dy. On the other hand, when it comes to z, partial derivative of this with respect to z, then these two are treated as constants. Therefore, constant times z, when you differentiate that partially with respect to z, you get the constant x y, right. Now, on the other hand, you can, if you have expressions like this, you can come in the reverse direction. How can you do that? Say in this case, you have all two, I mean sorry, just two variables. If you want to figure this out, there is a shortcut method of doing it. You take this term and just integrate this with respect to y, treating this as a constant. When you integrate this with respect to y, you have y. So, it should be x times y. Or you can just take this as well, and you can just integrate this one, keep this right. When you integrate this with respect to x, you treat y as a constant. So, y times x, yx. Even for example, this one, if you want to take this, how would you figure this function when you are looking at this? For example, you take this. Here the derivative term should be dx. Therefore, you have to integrate this with respect to x, treating y as a constant. So, you keep y squared as it is. When you integrate this one, you get x cubed. So, the function should be x cubed y squared. Even here you can play the same game. Here you have like here this free of x. So, if you integrate this, you have y z x. We have to integrate with respect to x. So, you have y z times x. So, x y z. And you can do the same thing with a term like this as well. Okay. Now, we have to go through one more important thing. Now, if you take an infinitesimal vector like this, how would you write that in terms of I, j and k? Now, you first project this onto a horizontal plane. Now, the vector we are interested in is p q. So, you project it onto the horizontal plane containing p. So, that is p r. Now, project that, or you can straightaway project that to a b, that is also possible. You project p q onto a b. Now, if you project a b onto onto the x axis, this infinitesimal changes dx. So, this vector is I dx. Similarly, if this is dy, that is j dy. So, a b should be I dx plus j dy. Since a b is parallel to p r and they have the same length, right, same direction, then p r should be the same, I dx plus j dy. Now, you can write p q as p r plus j d z, sorry, k d z. This is the z axis. The unit vector along z axis is k. Therefore, this r q should be k d z. So, you can simply add it like this, I dx plus j dy plus k d z. Since p q is equal to dr, now you can write it as dr is equal to I dx plus j dy plus k d z. And we need this in line integrals as well. If you want to find the work done by a vector field, you can figure this out. I mean, you need this one to figure out the work done by a vector field. Also note that in this problem, the problem that we are going to consider after this requires this relationship. Now, if you take the dot product with grad phi and dr, there should be a vector. This is grad phi, right. So, this is simply the grad operator, but you have to the phi, the scalar function phi falls in these operators, inside those operators. Dot, this is I dx plus j dy plus k d z, which is dr. Now, when you take the dot product, these two go hand in hand. I dot I is 1. Therefore, you get d phi over dx times, sorry, partial phi over partial x times dx. You have it up down there. Similarly, when you consider this dot product, you get this one. Similarly, in the last one, partial phi over partial z times dx. Now, we notice that this expression can be seen here. It is the total differential of phi. So, that is d phi, right. Now, let us get into this problem. Now, we will consider this vector field and we have to show that it is irrotational. That means we have to show that its curl is 0. Then you have to find a scalar potential phi such that f is equal to minus grad phi. We saw that the relationship in a previous video, the relationship between the vector field and the potential function, right. So, that is that relationship. So, now we need to show that the vector field is irrotational, we need to show that the curl f is 0. So, let us take curl f, put I j k in the appropriate places in the same order, then the components of grad operator in the appropriate positions, then the components of the vector field in the last row. Now, you simply evaluate this determinant, we did something like that earlier. So, I times this cofactor, it is this one, the operator should come first in the product, then minus j times these two minus these two. Here the operator should come first. So, you have that in the second line. Finally, k times this cofactor of this determinant, I mean after what you get after deleting the column and the row consisting of k. So, it is you have this product minus this one, you have it there. Then you simplify, here when you partially differentiate this with respect to y, you get this term is free of y. Here x is treated as a constant. So, the partial derivative of this is x here. So, likewise you can go through the other terms. We did something very simple, we went through something very similar to this earlier, therefore, I think an explanation is not required here. Since all the components are equal to 0, you get a null vector. Now, since curl f is equal to 0, f is irrotational. Once f is irrotational, you can find a scalar potential phi attached to the vector field, so that f is equal to minus grad phi. Now, there are two ways of doing this problem, but this is the easiest way, easier way. You take the dot product of both sides with dr, and we saw that earlier. When you get the dot product of grad phi with dr, you will end up with d phi, right. In the right hand side, this is how it happens, right. Of course, you have a minus sign in front. So, you have this as in that note given here, and this simplifies into d phi. That's what happening with the right hand side. Here I dot I is 1, therefore, this goes with dx, j dot j is 1, this goes with dy, like that you will end up with this one. This is the minus of the total differential. Okay, so that's what I have indicated here. The right hand side simplifies like that. Now, the left hand side. In the left hand side, when you take the dot product, I dot I is 1, therefore, this goes with dx here. Then y squared plus xz goes with this one, because j dot j is 1. So, this times dy, you have it here, but I should change it to dy. I have made a mistake there. And then this times this, like k dot k is 1. So, you get z plus xy times dx, dz. Right. Now, we will move to the line up there. There is no change in the left hand side, you have the same thing. As I explained earlier, the right hand side is simplified to this one with minus sign in front. What is inside the bracket is d phi, the total differential of phi. Now, this is a tricky part. Now, you gathered the terms consisting of one variable only. Now, look, 3 times dx consists only x. y squared times dy contains only y, z times dz contains only z. You separate those terms from the bunch. Now, take the other terms y z x, sorry y z dx, x times z times dy, x times y times dz, right. You keep that collection without any, without disturbing it. Now, you can write this as a total differential. How? As I explained you earlier, just take this term, right, integrate this only with respect to x. So, you have y, z and x, right. If you even you can play the same game with this as well, then you have to integrate this with respect to y. So, you have x z y, then put x z y there with d. All this summation is equal to the derivative of x y z, and we have the same thing there in the note earlier I explained you. Now, keep these terms as they are. In the right hand side you have minus d phi. Now, write everything in terms of a like differential of something. Now, this is the derivative of 3x. This is the derivative of y cube over 3. Y cube over 3, when you differentiate it, you get 3y squared. Those 3's will go away, you get y squared dy, like that. When you integrate it, it's easy to integrate it. Here, this is z squared over 2. Now, since d is, the derivative is linear, you can combine these two together. So, you have this one with 1d, a summation of these things. Right hand side you have minus d phi. Now, integrate both sides, you have all these things, but minus sign can be pulled out. Now, you have this one. Now, integrate it. These two will go away, leaving what you have inside. So, it is this one. But once you integrate, you have to put an arbitrary constant, that is c. Right hand side you have minus phi. Now, multiply everything by minus sign, and this is the function phi. Right. In fact, this is the scalar potential function attached to the vector field f given by this one. That is the physical significance of this function, right. And this is the easiest way of determining or finding the scalar potential phi, right. Okay. Thank you.